We have a set of a variety of different topics and in our portfolio, and it's important from our program perspective to really show and be very proud of the results we have in project. Usually we're shy about our results, we don't show off, but it's very important. I mean, we have to be realistic, not oversell, and really be to stay credible, but it's also very important to explain to the people, to the politician, to the citizen that, okay, we are investing here money in good things and have good results. So please be proud and sell your project. So we have a set of projects from medical to oil and gas inspection, flying robots, robots for manufacturing for SMEs, and then more research-oriented, still with some application strands, which is a long-term autonomy of robots, and the WEARABLE, it's about haptics and wearable, and then experience is a more research project to go into the learning from experience or learning in robotics. So first I give the floor to Ariana and Professor Meltzer to present Futura. So.
Yeah, thank you very much. So Ariana Menciasci was the coordinator of the project, and I was in charge of the medical coordination. So we formed a very nice and effective team to meet the unmet clinical needs. And what was our purpose? To close a gap in the area of treatment, to destroy tumors. And one of the most promising technologies is focused ultrasound surgery, which is a transmission of high energy into the human body without any cut or insertion of any catheter device. That's why we call it non-invasively, but still causing tissue ablation, destruction, and later a necrosis, which we want to see in medicine when we want to destroy tumorous tissue, but keep the healthy tissue alive as much as possible. So there are certainly kind of energy deposition is a mechanical energy, is a sound wave that creates heat, basically due to friction. And there's also a non-thermal effect, which you may know from ultrasonic cleaning baths, where you see tiny little micro bubbles, it's called cavitation, appearing that mechanically disrupts tissue. It has a very high level of safety because it's not entering physically the body through a cut, and it has a very high target precision. So in the history, as I said before, focused ultrasound was used, and we had several applications. None of them were really very successful over the years, mainly due to the lack of control where exactly the focal spot sits and exactly to avoid tissue damage of those areas we don't want to tackle. There are two ways to apply focused ultrasound surgery. It can be done, of course, with ultrasound control to position a certain target, and later in the 90s, there was a development of using the focused ultrasound inside an MRI scanner, and you see there is a huge increase of use over the time and a very rapid growth now because of evolving technology on both sides, focused ultrasound as well as diagnostic ultrasound. You see here an overview from the FAS Foundation, American organization that deals with the use and supporting the clinical use, and you see a huge variety of applications. There seems to be almost no barrier, but very important for us in medicine. You see FDA approval and what we are all not quite happy, reimbursement. you see there's no reimbursement really. There are some ways to get money for these procedures, but this is still a lag, but we have approved techniques available in MRI-guided focus ultrasound as well as ultrasound-guided focus ultrasound. So why is there then a need to develop? Current systems are limited only for a certain dedicated target or in a certain technical arrangement for prostate use or breast cancer, and it's not cancer, it's breast benign lesions. We are very careful in treating cancer because we really have to know about the cancer treatment, and it is a time-consuming procedure. It lacks a bit the flexibility, the use, the imaging is not entirely appropriate, and most important, we have no real option to monitor exactly the procedure. So the plan was to use robotics for much more precise positioning, to use a diagnostic ultrasound probe, state-of-the-art from any ultrasound vendor, and then especially developed confocal probe for therapy, for applying the focus ultrasound, and diagnostic ultrasound for monitoring. And the problem was to have both robots working accordingly in the same area, but also working on a human, and humans around the robots, as you all probably well know, one of the key issues to use these robots in medicine. This is a setup with conventional robotic arms, and you see here in the animation how the procedure works, controlled via optical navigation. Also Kinect is included, and this is was a concept of positioning in the kidney tumor imaged by the diagnostic ultrasound and then targeted with a focus ultrasound, also allowing compensation of respiratory motion, which is a problem of these intra-abdominal organs. So here were a lot to develop to make this happen. There's a bit of a competitive product, not really competitive, is a linear accelerator positioned by a robot arm, also compensating motion of the patient, but using aggressive ionizing radiation. The difference to focus ultrasound is it's non-ionizing radiation, has no cumulative dose, and can be applied in iterations and many times without harming the patient. Also, the energy deposition is very efficient, is 98–99%, whereas even in the best proton therapy system is not more than 90%. So, and a lot of side effects appear in radiation. So, a huge benefit for ultrasound. So, we want to, in comparison to the CyberKnife, use an ultrasound-guided focus ultrasound delivery. The treatment was very important. So in these interdisciplinary medical projects, first the medical people have to identify the unmet need, then the way things can proceed, the procedure definition, and we worked according to medical device regulatory pathways. So we have a pre-treatment imaging, registration, target identification, also learning about motion, therapy planning, then the treatment itself, target identification, sonication, lesion assessment, and then the evaluation of the treatment. And this then combined with other conventional medical imaging, pre- and post-operatively MRI and CT scans. So this was the starting phase. Now I hand over to Ariana.
So thank you, Andreas, for the introduction. The first point was to find ad hoc models for the assessment of the procedure. It is essential in a project like this where you cannot go directly on living tissues, and so we developed many different models for testing the accuracy and effectiveness of the therapy, in vitro phantoms, ex vivo tissues, and also porcine, kidney, and other embalmed organs with perfusion in order to be sure to have an effective evaluation of the therapy. Then the first part is the pretreatment. During the pretreatment, we have a 3D ultrasound scanning. Then we have the organ registration with image fusion between the CT scan and the ultrasound online imaging, and the therapy planning to identify the window, the ultrasound windows to have the therapy and the monitoring of the therapy. The second part is the treatment. The treatment has been done on static target to evaluate the precision and the overall procedure. And so we found a solution to have the continuous monitoring of the lesion also during the treatment by playing with a different window of activation of the therapy and switching off for seeing with the other probes the lesion growing. The treatment was also done on moving target by using tissues on sliders at 1 Hertz approximately, just to simulate the breathing. And we were able also in this case to have a good treatment with good accuracy by identifying a ROI of interest and following this ROI during the therapy. The treatment is also possible between obstacles, for example, ribs that are a sort of shield for the organs, because the transducer was fabricated in order to switch off and switch on some annular part of the transducer, and so to enter between ribs. And for the users, it's very easy to understand if the lesion is possible or not, depending on this online simulation, giving different colors to different areas and position of the robot. So the post-treatment is the assessment of the lesion that can be online by using ultrasound that is already integrated. It was done also in phantom and ex vivo tissue with an optical assessment. And as the very final result, the final shooting accuracy after offset compensation, so after the first shoots, was less than 1 millimeter. And less than 1 millimeter is very good because it is inside the cigar shape of the focus of the focus ultrasound transducer. Other implementation for managing safety during human-robot cooperation includes the use of Kinect sensor, also for having an online simulation of the robot's position, and a smart sensorized polymeric skin to be used around the robot, the ABB robot, to be have safe contacts in case of accidental contacts. So finally, we set up a novel robotic platform for ultrasound-guided focus ultrasound and also validation workflow. This was a major result of the project. We assessed the functionalities in vitro and ex vivo with dedicated models for targeting, syndication, and lesion monitoring. The very last slide is this one. This is technologies not only for clinicians and roboticists, but also for novelists. John Grisham published this very small booklet, The Tumor, that is a sort of presentation of these technologies that was he was really fascinated by this.
Thank you so much. While we are switching PC, we have time maybe for one quick question. Any question from the audience? From the content, from the exploitation of the project? Oh, there's one question there.
Don't you be back on HDMI?
And a very nice project indeed. My question is if it would be beneficial to close the loop by having sensing devices that could measure the heat transfer to healthy tissue to add an extra level of safety to not harm healthy tissue while you do the treatment? Thank you.
Yeah, this is what also indicated in the beginning is a problem. With MRI, we can measure temperature very precisely, but we have a very confined, highly regulated environment, and we wanted to develop something that can be used in an OR or in a treatment area. And ultrasound has an option to image the hardening of the tissue. It's like the egg white cooking. The soft egg white becomes hard, and the technique is called sonoelastography. It still is a bit of a delay, but it's equivalent to temperature. A certain hardening of a tissue is based on a temperature change. It must be at least 60 degrees Celsius, and you can see the process. So that's what we want to implement, and that's why we were suggesting to use a really high-end conventional diagnostic ultrasound to monitor, and all these machines have this available, and they're in all the hospitals. So we don't have to develop this as an extra tool. But you're absolutely right, the real temperature mapping on-site would be beneficial. Perhaps to say that MRI temperature mapping is not measuring the temperature, it's measuring the proton shift according to temperature change. So there's no direct measurement in both worlds.
Thank you again.
Thank you.
So the next presentation is by Chiba Buma. So the floor is yours, Petrobot.
Thank you. Good morning, everybody. It's a pleasure to present the Petrobot project on behalf of the consortium. We switched to a completely different domain. Our creations are pressure vessels and storage tanks in petrochemical industry. And we've been developing solutions for those applications. So the consortium that we had for Petrobot consisted of the full value chain. So we had end users, Shell, Chevron, Gasco. We had service providers, we had technology developers from, I think, 6 different countries. So the objectives of Petrobot were to provide robotic solutions to inspect pressure vessels and storage tanks. In our industry, inspecting those assets is a major cost driver, not because of the inspection costs themselves, but because they're very disruptive for the normal operation of the plants. So the plants have to be taken out of service, product needs to come out, these vessels and storage tanks need to become safe for human entry at the moment, and even then, entry in such confined spaces inherently is a risky procedure. So quite a lot of effort needs to be done to make that happen. So it's an ideal application where we can, in one stroke, both save costs as well as increase the safety. So it's not that often that you come across situations where you can do both at the same time. Usually, if you want to work safer, it's more costly. So robotics provide a unique opportunity to change that. As you will see from the project objectives, it's not so much only a technical development project, although we did a lot of technical development. It's really bringing the value chain in place to actually deliver these services to the market. So we were quite ambitious on the market side to actually not only develop these solutions, but also make sure that they could be delivered at the sites where all these assets are. So the gains that we want to have from that are, of course, minimizing the exposure of personnel. Risk scales with the amount of time that you're exposed to something. Well, if you remove personnel altogether from confined spaces, the risk goes down tremendously. Also, we can work quicker, so we can reduce downtime, which is an enormous cost driver. And of course, we can also reduce costs in all sorts of associated measures, like isolating the vessels to avoid dangerous gases from entering, cleaning, scaffolding, all those kind of things. So, quick look at the solutions that we developed. So this is a tank inspection solution. So this robot is lowered into the product and then semi-autonomously scurries around the bottom and does the full inspection of the tank bottom. So this was mostly an integration project where we married a submerged robot with inspection technology and also with cameras, and then also added a navigation system to make sure that we knew where we're doing the inspection. So there were 3 companies in the consortium that have worked on this. And this is how you deploy a tool like that. So it has to be hoisted on top of the roof of a tank, and then you lower it through a manhole into the tank, and it does work from there. So we tested this also as part of the project, also to develop the operational safety procedures that are needed to deploy such robotic systems. On the pressure vessel side, we developed a couple of different platforms. This is the bike platform, as it's called. So it's a small, versatile robot that can maneuver over obstacles and do quite complex tasks inside pressure vessels. Another platform that was developed was the fast platform. So on the left-hand side, you see the prototype that has been developed in the course of the product, in the course of the project. So it's not only the robot itself, but there is a navigation system on top. There's a special camera that was developed as part of the process. And on the right-hand side, you see the commercialized product that has come out of this as a result of the product. So that also shows that we were able to make the step from having nothing to having a working prototype, and now this has resulted in a commercial product that's available to the market. So what I would like to do now is play you a video of the pressure vessel side of the project. It has 2 advantages. In a few minutes, it gives you a clear overview of how we went about the field testing, and it also gives the opportunity to people in the video who worked hard on the project to present the bits that they've worked on themselves. So if we can start the video, don't know if I can start it from here or it needs to be started from, there we go.
Hello, my name is Prashant Potnis. I work as Inspection and Integrity Engineer at Shell Global Solutions at Amsterdam. In Petrobot project, I am leading Work Pack 3, which is about robotic testing in rear field pressure vessels. We are giving robotic developers and NDT developers an opportunity to do robotic testing in rear field pressure vessels. We are giving them this opportunity because they can learn about deployability aspects and inspection challenges of robotic inspection. Because of this test, we will be having a working solution, that is a robotic platform on an NDT tool like camera or structured white light or eddy current or ultrasonic testing.
I'm Moritz Oettiker. I'm a development engineer at Awesome Inspection Robotics. Basically, we provide robot platforms, the fast platform and the bike platform. The fast platform is a magnetic crawler robot. It's specially designed to go into confined spaces. What makes it really special is the laser rangefinder we have here. This is a rotating device. It generates a 3-dimensional picture of the environment, a so-called point cloud. And based on this point cloud, the operator can actually see in 3-dimensional space where the robot is located.
We move into the correct position, and then we set the exact position of the crawler, and that is based on where we put it in. We start up the laser that builds up the data cloud, and that gives this picture.
We always know exactly in 3D coordinates where the robot is, and that also enables reproducing inspection data so that we can actually find the very same spot again after a day or even after years.
My name is Barent van den Bos. I'm a project manager at Dekra Industrial in Sweden. Within the project, Dekra has worked closely together with the robot providers, partly to, of course, to learn about robotics and to learn about the possibility of robotics. But as we are NDT specialists, we also developed some NDT tools to be used on the robots.
We have developed a camera for this Petrobot project, and the camera has been designed together with the influence from air to make sure it fits onto the crawler. So, the camera is a high-resolution camera to enable zooming into a very far distance.
My name is Andreas Schleer of Innospection Company. We are responsible for the eddy current system of the FAST platform. Here we passed a weld, and a weld usually gives a strong signal, which is shown here.
One advantage of working in a project like this is that you learn about several types of requirements and can incorporate that in your solution at once. For example, the bike, which is a very light tool, a light robot, I should say, with a very good maneuverability. It doesn't have the high payload that the other robots have. So for the bike, we have developed very lightweight tools. We have a very lightweight camera to put on it, for example.
My name's Adam Mallion. I work at OC Robotics. I'm part of the Petrobot project. So OC is developing one of its snake arm robots for use as a deployment platform for inspection tools within the Petrobot project.
My name's Jason Curl. I'm head of mechanical engineering at OC Robotics. Key elements that's unique to the Petrobot arm is the articulating wrist here. The robot arm is self-supporting, so it allows us to go into tight confined areas.
I'm Jamie Wilkinson from OC Robotics. I'm a junior software engineer there. I'm just going to tell you a little bit about Sirius, which is our control software. Essentially what this is doing is that it abstracts away all the complexity of controlling this snake arm robot and all the degrees of freedom that it has.
We have other end users as our partners in the Petrobot.
In view of time, I cut it a little bit short. Let me come to the key success factor that we feel made this project very successful, and that is that we had the whole value chain in the project. So we started from the end user needs, so what is needed for inspection of these pressure vessels and tanks, and work our way back from how we're going to deliver that solution to the market, working with system integrators, with robot builders, with NDT specialists and service providers to make it happen. So because of that, and because everybody had interest in commercialization, we had perfect alignment in the goals that we were after. So that was, in our view, the most critical success factor of this whole project. So what were the achievements then? Indeed, we made working robots available that are now also commercially available on the market. We not only made the robots, but we also developed all the operational and inspection procedures that are needed to actually deploy these robots. We did a lot of testing, and of course there's a lot of changing in habits and in work practices to be done, so there's a lot of influencing to be done at all levels in the organization. So, but it has been successful, and there's now deployments on the go. The robots have been offshore for Statoil, the robots have been deployed by Chevron, by Shell and others. So the market is starting to develop around these solutions. And in the process we were able to mobilize the value chain. And that has now also resulted in a permanent platform which has been spawned from Petrobot, which is called Sprint Robotics, which is a global organization that is pushing inspection and maintenance robotics. You can also see that we had active interaction with Robotics, which has now resulted in a flagship theme, which is inspection, maintenance, and infrastructure. So all that would not have happened if it weren't for the Petrobot project. So we are still continuing not as a consortium within Petrobot, but certainly within the Sprint Robotics platform, and we are engaging with the world to show what needs to be done to bring these solutions to the market. And the next opportunity to have that discussion will be at Chevron in Houston. So end users are still actively engaging with the industry to show the need and the urgency of bringing those robotic solutions to the market. And you're all cordially invited to join us in Houston in a couple of weeks' time if you have time. Thank you very much.
So while we are doing the transition, maybe you have one question for Chiba?
Repeat the question, please.
Yeah, I was thinking whether you are thinking about extending the range of domains that you are including in your inspection and maintenance, for example, mining.
Yeah, absolutely. Of course, the logical starting point for us was oil and gas because that's where Petrobot started. But the remit of Sprint Robotics is definitely anywhere where there's capital-intensive infrastructure. So that can be public infrastructure, that's power generation. Rolls-Royce has just joined the organization. So yeah, we definitely intend to increase our scope beyond oil and gas. So if you're interested, by all means, join us.
Yeah, and if you have technologies also that can be used, yeah, join them as well. And thank you also for the Petrobot team, which came with cheap.
Yes, the supporters are there.
So thank you again.
Good morning, my name is Davide Scaramuzza, and today I'm going to present the results of the FP7 project titled sFly, Swarm of Micro-Flying Robots, of which I was the scientific coordinator. We are going to look back at this project after 5 years. So I would like actually to highlight all the impacts that this project had over these past few years. The sFly project actually ran, it was a STRAP project, 3 years and a half actually, that ran between 2009 and 2012. And the goals of this project was to develop autonomous swarm of drones technology that could help search and rescue team in the aftermath of disasters, like, for example, tsunamis, earthquakes. So one of the main goals was to develop drones that could actually navigate all by themselves without any user intervention, but only using onboard computing and sensing. And the idea was actually to be able to reach places that were out of reach for humans, and especially teleoperated drones. One of the main features of the sFly project was actually that the main sensing modalities were all based on vision sensors. So we had no GPS, we had no lasers. The reason why we decided not to have any GPS is because when you enter a building, of course, the GPS is not available anymore. So you have to be able to only rely on onboard sensing in order to navigate completely autonomously and explore unknown environments. We didn't want to rely on lasers as well because, of course, lasers are very power hungry and also very, very heavy, still nowadays. Within the sFly, what we achieved was that we were actually, our team, the sFly team, was the first to demonstrate vision-based autonomous navigation on drones, and using only fully onboard computation. So we actually at the time had an Atom board, later replaced by a Core 2 Duo. And what is interesting is that the results of this project inspired many other drone companies today, like Parrot, DJI, Unique, Skydio, and many other ones. The budget actually at the time was pretty small. It was, the total EU contribution was 2.5 million euros. And the consortium basically was composed of 4 countries and several members. So the principal investigator was Roland Sigvart from ETH Zurich. Then there was a computer vision lab led by Professor Mark Boniface, the CSCM, which is the Swiss Center for Electronic and Microtechnique. Then there was the group of Christian Loger at INRIA Grenoble. Then we had the group of Elias Kosmatopoulos at the University of Crete. And then the industrial partner was Ascending Technology that now became Intel. It was acquired by Intel last year. Now I would like to highlight the main project outcomes. I would say that the first main project outcome was actually the Asctec Firefly drone. I've seen actually here also the drone in the exhibition. Over 1,000 of these drones have been sold over the past few years. The drone was actually designed during the European project, and then it became a commercial product around 2012. It was actually also the first drone to feature visual inertial state estimation and mapping, also called visual inertial SLAM. At the time, you could actually request the drone with an additional camera, and the software was already open source. I'll talk about the software later. It was actually also the world's first product to feature visual inertial SLAM. So nowadays, there is still no other drone that does visual inertial SLAM. They do actually visual inertial optical flow, but they don't really build maps. There is now the DJI Mavic that is proposing actually visual inertial SLAM for the next round of products. The Asctec Firefly was basically an hexacopter. The reason why it was an hexa and not a quadrotor was actually to have a redundancy so that in case of failure, one of the rotors, the other 5 would actually take over. Later, Asctec partnered with the Skybotics, a startup from ETH that developed the visual inertial stereo sensor. Probably some of you have used it. And Skybotics later was actually bought by GoPro Switzerland. What you see now in this video is actually the latest iteration of the Asctec Firefly drone, where basically they replaced the stereo camera with the inter-reascence technology. So it's an omnidirectional structured light sensor that allows to do high-speed navigation and mapping. So this one was actually presented at CES Las Vegas in 2016. And they can be bought together or separately. Another main outcome of the sFly project was the ROS MAV software that was released already in 2011 on the ROS website. ROS is the Robotic Operating System. And basically, it's a set of small software that do both visual inertial navigation, especially visual inertial fusion, mapping, and localization, that has helped dozens of research labs across the world to start working on visual-based drone navigation. And what I think is interesting to highlight is that some of the visual inertial state estimation algorithms developed during the sFly projects are now part of Google Tango phones. So, for example, Simon Linen, who is one of the key engineers at Google Tango, was actually a PhD student during the sFly project. And also Agostino Martinelli, who was actually one of the lead researchers at the IRIA Grenoble, developed a closed-form solution for visual inertial state estimation, which is nowadays used to initialize all of filter-based visual inertial solutions. Another great impact of the sFly project probably is the PX4 and Pixhawk Autopilots. It was established by a PhD student of ETH Zurich during the sFly project. His name is Lorenz Meyer. And basically, it's a software and hardware platform for drones. So it includes IMU, sensor fusion, and motor control. And you can actually look at the PX4 and Pixhawk Autopilots as the Android for phones, so like an operating system for drones. What has been the impact of the PX4 and Pixhawk Autopilots? Well, it has been sold on more than 500,000 units. Actually, it was not sold by ETH, but rather by 3D Robotics, because this was an open software and open hardware project. So there was actually no profit from ETH. Everything was released open source. It's actually being currently maintained in partnership with Qualcomm, ST Microelectronics, Intel, Bosch, 3D Robotics, and many, many startups. And is especially supported by dronecode.org, which is basically a repository where all the people working on drones can actually upload code that can be used to run on drones. So not just autopilots, but also path planning algorithms and vision-based algorithms. And drone code is actually supported by the Linux Foundation. Another interesting thing is actually the impact it had on academia. So the PX4 has been cited in over 1,000 publications. And in this picture, you can see only a few of the drones, commercial drones that are using the PX4 today, like the PhotoKite tether drone. There you see Raffaello D'Andrea playing with the flying lanterns, which is now part of a show in Broadway since 1 year ago. A TED Talk, also the 3D Robotics, and then also Amazon Prime Air is using Pixhawk. I would also like to highlight that 6 former sFly members are now successful professors worldwide. So these are the 6 people. We have Laurent Kneip, who recently became assistant professor at the University of Shanghai. He actually did significant contributions on geometric vision, like 5-point algorithms, 3-point algorithms that you need for Visual Slam. Stefan Weiss was actually one of the first employees of the sFly project. And after the sFly, he found a job at NASA JPL. And actually, he ported some of those algorithms on the drones that one day will probably go to Titan and Mars. Then Friedrich Frondorfer became a professor at TU Graz. Margarita Klee became a professor at ETH Zurich. Myself, and also Kim Hee was recently appointed assistant professor at the National University of Singapore. So I think it was a terrific success. I have to say also that I want to thank the European Commission because it was also a tremendous success for my group. I think without the sFly, I wouldn't have gotten the success that my group had so far. So I think all my research actually was basically inspired 100% by the results of the sFly project. So in my group, we work on vision inertial SLAM, we work on agile flight, now also deep learning using only onboard sensing and computing. And that's actually one of the things that I think the sFly was really introduced. Also, the sFly project inspired one of the recent products by Parrot, the Albris drone, that basically uses visual inertial SLAM to do vision inspection, autonomous vision-based inspection of bridges, power masts, and power lines. The DARPA FLA program, Fast Lightweight Autonomous Program, that is the first DARPA challenge that focuses on high-speed, GPS-denied autonomous navigation of drones in cluttered environments. And with this, I would actually like to conclude and actually give the words to Anibal Ollero, who will witness some of the contributions of the sFly. Thank you for your attention.
So thank you, Davide, and thank you, Cecile, for the invitation. Just a few words about a couple of projects, earlier robotics project that concluded last year that I was coordinating. The first is ARCAS. ARCAS was a project in which we have, I think that we play a, let's say, seminal role in aerial robotic manipulation. So we developed the very first aerial robotic manipulator with 6 and 7 degrees of freedom arms. We also developed in this project embedded perception and planning capabilities to manipulate while flying. So that means that this was a success of this project that was also quantitatively have significant impact. Only during the project we produced a large number of publications. I think that was 130 publications. And then we generate some hundreds of citations from the last year. And I think that this was also some success in terms of technology transfer. Some of the functionalities combining radio vision, computer vision, have been used to positioning of machines indoors in some factories, particularly in Airbus factories, and we have been developing this concept also in other projects. Additionally, in the second project that I was also coordinating last year, we developed a number of, this is more industrially oriented, we developed landing systems in which we were able to land on mobile platforms, that means chips, and also cars, fixed wing landing on cars. So that means that we have transferred this technology to a company working with us in the project that got contracts to land on chips, on vessels of the chips, and then we transferred the autopilot and the landing system to this company that got contract for some millions of euros. And also we developed technologies for surveillance that have been also used by other companies in terms of frontier surveillance and sea border. So that is something that we develop now, we are developing now. I also want to conclude saying that there is strong interest around the world. So there is some demands from implementations in Asia and also in the Emirates. So thank you very much for your attention.
Thank you so much. Congratulations, that's really an excellent example.
Thank you very much. My name is Martin Hegele. I'm very happy to present to you our project, our SME Robotics initiative, which we have actually started in 2012 and which was then finished last year, end of June. And in fact, SME Robotics had its predecessor, which was called SME Robot, and the SME Robot project still was an FP6 project, was fundamental in the creation of safe human-robot interaction. And today, when you see the safe controller, which now is offered by almost all of the robot manufacturers, so most of that, or a good deal of that work was actually achieved in SME Robot. And we, of course, thought about the continuation of this effort, and quite obviously, not only working safely with the industrial robot is of major importance, but also the intuitive interaction with a robot was of major importance. And in fact, here you see the vision and the mission of our SME Robotics initiative, and the major goal was to bring cognitive capabilities to industrial robotics and cognitive capabilities to actually work with the robot intuitively and also have the robot interact or execute tasks when encountering uncertainties of any kind. Uncertainties can come from products, product tolerances, from process deviations, from environmental changes, but also from, for instance, lagging of digital data or changing throughputs. So all of these actually make up uncertainties which are difficult to handle, especially given some degree of automation. And all these uncertainties are extremely typical, actually the major aspect of SME manufacturing. So you have seen that we actually wanted to deal with any kind of uncertainty which may occur in manufacturing practice, that we actually wanted to integrate the human operator in a very intuitive way, that we wanted to embed cognitive capabilities to the robot, actually to use digital data as much as possible, and that we also can integrate robot systems with peripheral devices based on plug and produce capabilities. And you see actually already here one way how we try to solve it by semantic integration. So when we talk about the use of robots, of course, industrial robot is very effective when it actually can access already digital data coming from product processes or other production-related data. However, in many cases, these digital data are not available or inconsistent or maybe not on the current state. But in any case, we should try to work as much on existing digital data as possible. And if it's not possible to actually generate program out of digital data, we should have engaged in a goal-centered user dialogue. And this is actually one of the major topics which we encountered, that we actually have to engage the user in a very intuitive way. And there are three modes which we concentrated on when integrating the user. Of course, the automatic generation of robot programs is the most effective way because it's done automatically, maybe under lot size 1 conditions. But important way to actually interact with a robot is to work on CAD data, to actually look at the task, actually use the task given constraints, given processes, etc., to actually formulate this on a screen, on a graphical interface, or the last resort is that we actually do intuitive on-site instruction. And it's quite important that we can actually switch between these kinds of operative modes. And of course, we also want to use back these gathered information, this gathered data, and we did that successfully, especially on the level of process data. For instance, when it comes to drilling, of surface finishing, etc., these are important processes where we actually can already use the results from the actual task execution to feed back into the planning system when it comes to working with skills or other control primitives to effectively execute the task. Another important aspect of SME robotics, SME manufacturing, is of course the cost effectiveness. And for that, we actually developed also a tool, a web-based robot investment tool, which gives the end user, a possible end user, a very quick assessment of is it possible and how is it possible to actually go for a robot solution, and who are the actors who can actually provide solutions. So we have an abundance of video material which you may access on our YouTube channels. However, here's a very, very short impression what SME Robotics explained in 100 seconds. And here you see, for instance, why we need cognitive capabilities to locate, to identify workpieces, to identify or access environmental conditions. So the interaction via graphical interfaces. And one major aspect is, of course, also the error treatment. Very often there may be quite errors or deviation which may occur, and also the operator has to be, has to actually deal with the correction of some kind of deviations or error sources. In fact, it's quite interesting when you look at the more or the longer video material, also the way how the role of the worker changes. So the worker becomes much more an intermediary between digital information and the actual process execution, like a conductor in a manufacturing scenario. So this is very interesting, and also the trade unions were extremely interested in the material and the experience from the actual practical solutions to actually generate a vision of future skills and also workplaces a worker in advanced manufacture will occur. One specialty for us was also the design of the project, and so since we had to deal with software components or software in general, the idea was how do we develop the software and how do we actually package it to make it available to others, users, end users, system integrators, etc. And so we thought we have to aim for packaging components and actually developing and verifying these components on existing test beds. These test beds were then transferred into full-fledged core demonstrators, and after the test bed phase, which was beginning of year 3, we also launched a so-called call to invite other teams, other end users and system integrators into the consortium and actually use these components and reach out into new application areas or new industrial processes. So, and we call these kinds of demonstrators supplemental demonstrators, and the team was usually made up of a researcher or system integrator and an end user. Of course, also for us, the reach out was very important, and to actually give enough reasons to believe for picking up these components by possible end users. We actually launched, displayed the test beds at the Automatica 2014, and after the Automatica process, we actually had the teams, the supplemental demonstrators teams, invited and actually add 4 further supplemental demonstrators to the project. So this is a very short impression on the Automatica. You see the former commissioner here for the launch event. It was, of course, a tremendous show. And so these were the supplemental demonstrator teams coming from different applications, different industries, which actually used the components, the modules developed in the first phase of the project, and actually made new instances of the results. So, and the final result, or the results, were actually displayed in real factories, assessed in real factories in production environments, but also we had the final showcasing of the project at the last Automatica 2016. Again, it was a tremendous show, which also emphasized that the one of the major impacts of the project was also to reach out to not only to end users, to system integrators, but also the general public. So this was certainly a tremendous success. And also we reached that SME robotics somehow became a trademark in this kind of research towards applying industrial robotics technology in new domains of industrial manufacturing. So what the results were, of course, we had 29 identified results, which were actually transferred into products or software components by the project partners, but also, which was certainly a nice aspect, was that 3 startups were actually generated during the project runtime or immediately after that. And yes, we, of course, had tremendous outreach, also the general public, and also scientific impact. And here's some of the numbers given on the slide. So that's basically it.
Perfect.
And
thanks. So while I'm just checking, thanks a lot for the presentation.
So, good morning, everyone. My name is Nick Hawes from the University of Birmingham. I'm the project coordinator of the Strands project. It's an integrating project, FP7. We've got a couple of months left to run. And thank you, Cecile, for the invite to talk here. It's a real honor. And I just want to say a really big thank you, actually, to the whole Strands team. So a few of you are here. And what I'm going to present today is really collaborative, integrating work. And it wouldn't be possible without the excellent and very hard work of the whole team. So thank you. Thank you to everyone. So we were asked to present kind of what was sort of novel, interesting, the vision behind the project to kind of motivate us to being one of these success stories. And so I'd like to share with you the sort of vision of the project that we tried to embed in everything we did within the Strands project. So the idea of the Strands project started from the end goal of a lot of our work, which is we want robust, intelligent, and autonomous systems to work with. In particular, we're interested in mobile robots, but what I'm going to talk about in the general terms applies to everything that you're hearing about in this excellent event here. So we're ultimately interested in robust, autonomous, intelligent behavior. And we want that to allow our robots to do tasks for end users, but also we want them to be able to do tasks for a long period of time. So one of the other things that motivated us was actually some maybe internal frustration at previous projects where we developed really cool technology that ran for an hour or two to make a video or show a demo, but wasn't really being tested in the real world. It wasn't being used by end users for long duration. So a service robot or a robot should be some other bit of technology, just like a photocopier or a printer, and you want to buy one, get it to do the task, and forget about it. But we wanted to kind of challenge ourselves to achieve that and not have computer scientists hanging around the robot all the time to make sure it works correctly. So we wanted to deliver long run times with our autonomous behavior, but that wasn't the end. That was the beginning. What we really wanted to do is learn new things. Because when you put a robot into an environment for a long period of time, repeatedly doing the same task, repeatedly experiencing an environment, they now get novel opportunities to see the world in different ways. A robot that exists for an hour or two gets a snapshot of the world. A robot that can run for weeks or months at a time gets to really see different dynamics, different patterns in its environment and its working life that it wouldn't otherwise encounter. And that's really how we wanted to close the loop. So we wanted to learn things in the environment and exploit the results of learning in order to deliver both kind of more robust systems, but increased task performance as well. So that was kind of the cycle behind Strands, the vision that we had when we started the project. So what did we do to deliver this? Well, we really focused on deployments with real end users. So from the very start, what we were doing was putting service robots, so mobile service robots, into real environments with real users for long periods of time. That was how we were going to, well, that's how we have evaluated the success of both the overall project and the individual components. How well do they run? How well do they contribute to that overall vision? To do that, from the very start, again, we had to work on integration. We had to integrate planning, learning, perception, the whole kind of sort of cognitive package, effectively, into robots. Again, doing it in a task-driven way. So we're not doing blue skies sort of cognitive robotics. We're really focusing on robots that can work with end users. But in that, we had to do a significant amount of engineering. So to make the systems work, we had to invest an awful lot of time in making them robust, making them reliable, and putting the pieces together. So that allowed us to do 8 deployments. So over a 4-year project, we did 2 a year in facilities management, security, and care. And we've been running those robots for long periods of time. So currently, we've got robots, in fact, 2 robots, one in the Transport Systems Catapult in Milton Keynes, and one in the Haus der Barmherzigkeit, a care home in Vienna. And both of those have been there more or less for about 4 months, and they're still there and still going strong. So this is real exposure to end users to mobile robot technology. So what did we achieve over the project? Well, the biggest thing for me is that we did it. We can do it. We can put robots like these into real environments and have them run autonomously for months at a time without experts present. So these robots, we take them to the site, we program them, we leave them, and then they do their own thing. As they do their own thing, they learn, they get better, they improve their performance, and actually, people are very happy to have them there. So this is a great kind of sort of headline achievement, I think. But if we look in kind of more detail at some of the other things, the long run times have been great for us as well. So we've managed to do runs up to about 30 days of continuous autonomy, so with no expert interventions over that whole period. And that's been, I think, a significant advance in these kinds of environments. So we see autonomous systems operating for longer in other environments or with less complexity, but these are very complex autonomous systems in very dynamic environments. Sometimes people, I think, underestimate how challenging offices and kind of almost real-world environments are, but they're a real pain to work in. We also have done acceptance studies, and users are very ready to have these kind of robots in their lives, as long as they're doing something useful. I think that's the message we take from this. There has to be a really kind of business-critical task for these robots to do. And the robustness that we achieved is really only down to a lot of testing and a lot of integration. You don't get this for free, you have to put hard work in. Sometimes us as more research coders aren't up to the right standards, but what we lacked in maybe professional engineering ethics, we made up with enthusiasm and commitment. But that commitment paid off. So the robustness in our systems is what gets industry interested. So from a researcher's perspective, I want to see that pipeline, I want to see the value chain that you've heard about already, and that comes from demonstrating your results in real-world environments in of robust nature. And equally, the science payoff is great. So I think we're up to about 90 publications from the project. At least 30 of them are from integrated systems work, either from the robots themselves running algorithms in real environments for long periods, or from the data those robots gather. So there's a real scientific payoff from the long-term autonomy too. And of course, that robustness allows the robots to learn in the wild. So they're existing out there, and they're actually learning online in an unsupervised manner all the time. So to give you a very brief overview of what they've been learning, what they've been doing, and our project approach, well, one of the main interesting parts of the project has been trying to learn, detect, and exploit spatial temporal patterns. So here we're using a frequency-based model called Freeman from the University of Lincoln. And what we do is we take predictions from these spatial and temporal models, and we kind of combine them with probability and maps of the environment to build Markov decision processes. They allow us to reason about uncertainty in the environment and build plans for the robot. Those plans, because we're using the uncertainty, because we're using the spatial and temporal predictions, we can then navigate robustly around kind of varying environment features like doors. We can arrive at times and places to make repeated observations of the same parts of the world. And that also allows us then to learn things, so objects, activities, all in unsupervised ways. The robot's driving around, it's observing things, and then it's using this information to ultimately assist in its tasks. One of the tasks we did was information provision in a hospital, and there we showed that by learning and using spatial knowledge, we're able to improve the interactions with the robot, make them more regular across the duration, rather than losing interactions during sort of the lack of novelty. So we're really kind of closing the loop on that vision I showed earlier. And this result has also led us to a number of follow-on projects in kind of more specific application areas, logistics, underwater monitoring, and so we're really now building on these kind of more general results to build specific impacts in different domains. We also have a kind of project-wide publication that will be in RAM in the next year, so I encourage you to check that out if you're interested, and also we're in the demos downstairs, so you can come and see some of our robots. But now I want to hand over to Michael Ginger from Honda Research Institute Europe, who's going to be one of those users taking on the results in the Strands project, and he's going to give us a short summary of their interest. Thank you.
Hello, good morning. So my name is Michael Ginger. I'm work for the Honda Research Institute in Germany as a principal scientist, and we are one of the users of this nice results from the Strands project. And what we are mainly dealing with is cooperative intelligence, where we focus on the interaction between the human and the machine in the artificial intelligence scope. So we want to realize something like a trust building or intention recognition and things like that in the cooperation. So this is just showing like a rough diagram of what we are striving to do. So on the one hand side, if we look at a nowadays system, we have like systems that need a human to cope with the task, as we have seen nicely from the Strands project. There's also systems that can cope with the task autonomously, but what we want to achieve is a system that can, together with a human, solve the task and share the success. So this involves much more than autonomy, but also a trust building, acceptance, and intention recognition and such things. And why we find this Strands project very interesting as a basis for pursuing our research. So firstly, it has shown that there is a long-term autonomy really proven in some real environments. So the robots work in different settings. There is no engineers in place, and that's really remarkable. And on the other hand side, there is also a learning concept for learning from experience. And what we want to do is to make use of this system as a baseline system and investigate aspects like cooperative intelligence and also set up a multi-robot system that allows us to research the elements to cooperate with the human to solve tasks together. Thank you.
Thank you.
Thank you, Cecile, for the invitation, and it's for me an honor to present my project. I'm coordinating this project, and Giovanni Spagnoletti, who is the CEO of this spin-off that came from the WEARABLE project. We'll talk later on. So this is the consortium. This is a shot of one of our meetings. It's a project with 10 partners. And the idea is to establish the foundation of wearable haptics, wearable technologies. So the main idea was this one. If you look to the modality of the audio modality, so we have been see these kind of speakers that are able to work, of course, in rooms. But then at a certain point in 1980, there was a big technology step with this wearable technology. In fact, Sony Walkman invented this Sony Walkman, which was very famous for the headphone. So we went from the room desktop device to a wearable device. What we wanted to do is to do the same for haptics. So we wanted to go from desktop devices for haptics technologies that are robots that are able to apply forces on our body to simulate a virtual environment or to teleoperate robots. We wanted to go at the wearable level. This was the idea, to go from desktop to wearable technologies in haptics. To do, and this is mainly one of the results of the project. You see, you can, just to give you the idea, you have this sphere, and these wearable technologies replicates the tangent plane. So while you walk, you can also feel and perceive environments that can be virtual or remote. This creates new paradigms, for sure, in human virtual reality, human-to-human interaction, but also in human robotics interaction. So the idea was to establish the foundation of this new area of research in wearable haptics. Okay, so we developed a family of devices, family of scenarios. I don't want to go into these details. The model that we developed was this one. So thanks to the EU funding, we developed the research, and then we developed several patents, and thanks to these patents, we are now cooperating with the industry companies and creating startups based on the patents that we made. Okay, so this is the time. Well, let me talk about some of the applications. So I will talk about 4 applications that are different enough from each other to explain how wide is the range of application we can have with this wearable technology, with this wearable device applying forces. The first one is guidance view of blind people. This is a patent that is exploited by the Association of Blinds in Italy that have a set of companies who are taking this patent and using it. The idea was that, so if you have a blind that wants to walk in Edinburgh now, then probably you need a volunteer, and this volunteer should bring this guy around, okay? And because they don't want to use the GPS and the navigator, because they don't trust too much the satellite, and they don't want to have the headphone. So the idea was to bring the volunteer at his home, actually. The blind has a camera. The camera streams the images on the screen of the volunteer, and the end of the volunteer are on the forearm of the blind thanks to the wearable technology. So they are applying this kind of forces. So this kind of guidance, you see, there is my students here, and this student is now, he wants to turn on the left. Look at the index of his right hand now, just in a second. You see now? The signal arrives to the red wearable band where there is mechatronics applying forces, and it turns on the left. So it's very reliable guidance. This is actually, this was also another application in my lab, just to see. This was blind since she was born, and she's guided in this environment without knowing anything. Of course, she needs the white cane to avoid obstacles, but the tactile stuff is saying go left, go right, basically. Okay, the guidance is also very important in Industry 4.0. And this is my opinion. So humans, so robotics in 70s and 80s was very, very successful because actually the industry was a structured environment. So the robots know exactly where they had to go. If the humans comes into the picture, then everything becomes unstructured. Okay, so you have a lot of structure and predictable stuff. So what we need to do to have the same success in the industry is to put some structure in these humans, in the cells. How? Just to wear the wearable technologies in order to deal with humans like if they were robots. So if you look to all the cameras are able to see what the operator does, but is not able to suggest trajectory. Look just at this sketch. And this is an application that we are doing with TUM, one of the partners. This is one of our students, and he's following, thanks to this wearable technology, the trajectory that he does not know at all, and he is able to follow with these limbs, so not only with the body, the trajectory in the environment. In a certain sense, thanks to this wearable haptics wear-up project, we are able to write, to guide, to suggest trajectory to humans, so to deal with humans in industries, a little bit like if they were robots. Okay, and this is, ABB is really interested in this, and we talked about the wear-up project to the Expo in the main event of ABB in Milan. Okay, of course, there is another impact that is the direct cooperation, the direct teleoperation, direct hand. Typically, you see here some console. With our technologies, we can do direct hand, and we are using this in several scenarios, and also with several companies, and also is not only of course wearable, but because the wearable part also takes the cutaneous information that is very, very important, and we were able to attract into this article who founded our part of our consortium to develop this technology. You know that the Da Vinci does not have the tactile feedback, and we added this wear-up device on the fingertip to feel the device and to feel the tumors or some other tactile information you want to have. Okay, another important application before introducing the startup is the integration with the other limbs. So we were used to see teleoperation, okay, in general. So, but we can also think about supernumerary limbs and feeling external robots. Just to give you an example, this is also very successful. You see this subject. This is a stroke patient who is not able to move the right hand, and of course he cannot do bimanual task anymore. So the idea was very simple. In this case, of course, we cannot use the prosthesis. We don't want to use huge exoskeleton. We wanted to use just very simple stuff to realize the grasp, just one finger more. So we invented this sixth finger that can also, now it is a wearable bracelet that creates a grasp, just substitute something and let the subject to use the right hand like a gripper. This is very important for wear-up. Why? Because sometimes when you have a stroke, many times you are not able to perceive anything here because of the hyposthesia. So you have to reflect what's going on here on the contralateral hand. So we are using our wearable technology on the healthy hand to steer and control the wearable supernumerary limbs. You see this, I mean, we were developing this ring in the wear-up project, and this is just a running of the application with the wear-up technologies, and that is an application, for example. And this guy is able to, I mean, they are really enthusiastic to be able to do. There are coming people trying to do the mocha, the coffee. So that just to hold the base of the coffee machine and or to use the toothbrush and things like that. Okay, now it's just a few minutes to introduce Giovanni Spagnoletti.
Good morning to everyone. I'm Giovanni Spagnoletti, and together with other three guys that belongs to the SIRS lab group of the Professor Domenico Prattichizzo, we just started a spin-off from WEARABLE. So what we are going to do is to try to exploit the prototypes developed during the WEARABLE project in a virtual reality environment. In these slides, we can see our demo that we proposed at SIGGRAPH 2015. Here, the user is wearing our finger devices, our wearable device. In this case, the devices are only able to provide normal forces on the fingertip pulp. So in this case, as we can see, we have a lip motion controller to track the human hand. And while the human hand goes in contact with the virtual environment and with the object, we can provide the haptic feedback on the fingers. The last demo that we did was in November 2016. Here the device is different. Here we have 3 degrees of freedoms. So we are not only able to grasp the object and render the normal forces, but also exploring the virtual environment. More than this, in the platform that goes in contact with the finger, we had also a voice call to render the texture of the surface. So in this case, we can also explore the virtual environment. While we were, thanks to this demo, we won the Best Demonstration Award in Asia HAPTICS. And while we were there, we had also a face-to-face meeting with Sony, as they are really interested in our technologies to develop and to use this kind of device for gaming application. Thanks for your attention.
So this is the demo. It was running. And just to conclude, let me say that so we found in this project a new field with an exponential growth of papers on wearable haptics. So we developed a lot of patents, spin-off, a new generation of professionals that was difficult to get without the European funding. So in my opinion, one of the big outcomes of your big work with the European community is to generate really experts that are difficult to create in other way. And humans is a big potential for us in Europe, not only products. So I want to thank European community for these opportunities.
Wonderful. Thank you. Thanks and, good luck for your campaign.
Sure.
So last but not least, now we have Tamim presenting an excellent project too. So if you have one quick question during the transition.
Hi. Okay. Thank you for presentation. My question is about you're applying these haptic forces to the fingers or to the limb. Have you thought of applying this, for example, to multi-limb, to exoskeleton, or?
So there is an interest now to integrate exoskeleton technologies with wearable fingertip device. These are mainly cutaneous devices. So these are mainly skin stretch deformation device, while exoskeleton work mainly on kinesthetic device. So there is an idea to integrate both, but only if there is a need, because in my opinion, we need to minimize the number of wearable, the complexity of wearable technologies. So we are trying to understand when it's needed to have.
Excellent. Thank you again. And Tamim, the floor
Okay.
is yours for experience.
Okay, yeah, thank you very much, Cecile. So, hi everybody. I am going to present the results of the experience project, the project Robots Bootstrap through learning from experience, which I was coordinating together with Professor Rudi Gedelman from Karlsruhe. Here you see the partners of the project. So this is, in addition to KIT, the University of Göttingen, the Italian Institute of Technology, Joseph Stefan Institute, the University of Edinburgh, Innsbruck, and the University of Southern Denmark. What's about in this project? The project was about combining two approaches, actually, what we know in cognitive robotics, for knowledge extension or knowledge acquisition in robotics. So on the one hand, a developmental approach where the robot, which allow a robot to extend or to acquire grounded and robust cognitive representations about itself and the world in a data-driven way. And the other approach, which we use as humans, or which is the feature of our cognitive capabilities as human, where we use generative mechanisms based on previous experience for knowledge extension. So this is an inside-out process which is more model-driven. And the question was how to combine these two worlds actually in knowledge acquisition and to implement that in a complete system, humanoid robot system, which is able to reason about the world and to predict the consequences of its actions. So in order to do that, knowledge representation is a very important topic, actually, and this was taken from a previous project of the experience project. This was the PACU Plus project funded in FP6, where we have established together with this team a representation for object-action relations, so co-joint representations of perception and action. We call them object-action complexes, which combine the notion of affordances, formalize the notion of affordances, and allow prediction and reasoning. So these representations were taken as the basis, actually, in the experience project. So, so what we do actually, or what we did in this project, is to implement such experience cycle in which the robot execute or perform tasks in the real world, represent actions and the effects with the associated perceptual representations of objects as triples. These are object action complexes, still non-symbolic representations which are used in a generative modeling process in order to generate structural symbolic networks of knowledge which can be used in internal simulation in order to generate predictions about consequences of actions, where these predictions are subject to validation in the real world, and where this validation reinforce or weaken the generative modeling process. The main novelty of the project is what we call structural bootstrapping, which is an explicit mechanism for generative model construction used for internal simulation to extend knowledge. And this concept is taken from natural language acquisition research, proposed the first time by Gleitman, 1990, where you compare, or based on this concept, you compare newly observed entities to a model of experienced entities to understand novel situations and predict consequences of actions. And the goal of the project was, can we find something or transfer this concept to robotics, yeah? In particular to the sensorimotor domain in robotics, and devise a framework which allow us to improve and to speed up learning in robotics at different levels, on the sensorimotor level, but also on planning, symbolic, and even on the language level. So, and the goal was to use the concept of structural bootstrapping to define these generative mechanisms which use existing experience of the robot together with new observations about the world in order to supplement the knowledge with missing entities about objects, actions, relations, or planning entities, and enhance the robot capabilities. And here are some of the examples. Actually, the goal is, in a very simple word, to try in a sensorimotor domain, based on the sensorimotor experience of the robot, to find structure in this sensorimotor experience and to use this structure to speed up and or to improve learning. Here is a demonstration of the experience cycle performed by the group of Justus Pieter in Innsbruck, where the robot is actually implementing the cycle which I explained before, and bootstrapping the learning of complex object affordances in the task of building towers here. This is only just an example how these concept of finding structures in sensorimotor domain can help in order to bootstrap robot capabilities in terms of being able to reason about the world and to discover the learning order of actions which should be executed in order to perform a certain tasks, and where the complete symbols which are needed for planning, for symbolic planning, are generated on the fly from the sensorimotor representation. Of course, the project was motivated by an idea taken from natural language research, and here our colleagues in Edinburgh implemented a language-based full-scale demonstration of structural bootstrapping. So they actually introduced the first fully general language-independent and domain-independent computational model of conceptually grounded language acquisition by a machine and child, demonstrating both semantic and syntactic bootstrapping. They also developed the terabyte-scale text mining domain knowledge for robot applications, the ZS, and big database tools for fast wide coverage parsing and parser induction for people working in the language domain would understand what all these terms mean. And these developed language technologies actually in the project have been taken by several leading groups working in the area, and also in form of funded cooperative projects with Google. Of course, we did a lot of work on other things, like, for example, continuation and the new directions of programming by demonstration, segmentation, and understanding of human actions here by myself and Professor Dillman, and also very nice work on motor learning and combination of reinforcement learning and dynamic movement primitives for complex tasks like wiping tasks, but also bimanual lifting or manipulation of objects performed in the group of Alish Udi in Joseph Stefan Institute. And last but not least, we implemented a full integrated humanoid robot system which is able to perform complex tasks in a human-centered environment, where the robot is actually performing a complex task together with a human in interaction with human, preparing a dinner for two people, where the goal for a symbolic plan is inferred via a natural language understanding component. Once the goal of a plan is known, then a description of the word is automatically generated from the working memory in order to generate then the plan and to execute it, where cups, for example, has to be placed on the table, where a salad has to be prepared, where a role assignment is happening based on the capabilities of the robot, whether the robot is able to cut the salad or the human should take over this task while the robot is picking up the corn and pouring oil into the salad. A lot of sensory motor capabilities such as mixing were learned from human observation, for example, and complex bimanual tasks executed, as you see here, based on position-based visual servoing and learned dynamic movement primitives for wiping, but also for pushing and other tasks. And the most important thing is that the robot is learning from experience and, for example, replacing a salad bowl by a mixing bowl if this entity is not visible in the current world, or replacing a Coke by a multivitamin juice based on text mining information which has been generated and stored in affordance tables, where the robot can propose to offer an orange juice if a Coke is not available, for example, in the world. As you see, this is a very research-driven project, actually, and I'm happy, and all of us were happy, actually, that we had the opportunity to work on these scientific research questions. And the project generated a lot of scientific and technological knowledge. Here you see a few examples about what has been taken over from this project and used in other existing or running projects in framework in FP7, but also in Horizon 2020. For example, the oak concept, which has been used only for grasping, has been extended in the Walkman project in order to deal with balancing and whole body manipulation tasks. We are actually working on the extension of representations of object action complexes with temporal information in the area of temporal cognition in a FET proactive project. Much of the architecture, which I haven't presented today, is part of a second-hand project in which we are developing assistant robots for maintenance tasks in warehouse environments, and many other topics, as you see here on the list. One, for me, very important thing is actually the transfer of these grasping capabilities of our robots in a kitchen environment to a very important area of intelligent prosthetic devices, where we are working with a big company in Germany in a national project and several SMEs on the implementation of semi-autonomous grasping capabilities for prosthetic devices. Let me show you just a few examples from the Walkman project, where the robot, based on its representation of the world, as you will see here, what the robot is observing and perceiving, is able to reason about which actions can be applied on which entities, like liftability of the pipe, like turnability of the valve here. And all these, what you see here in this demonstration, actually what has been shown at the last review meeting of the Walkman project, has generated based on these object action representations, what you see here, where all these affordance hypotheses are visualized in a pilot interface here, so to allow the user to select the action and adapt the parameter of the actions before the execution of these tasks in semi-autonomous operations like in rescue or disaster situations here. Another example here is the Imagine project, a project we started this year. Justus Pieter is the coordinator, and I think he presented yesterday the project where it is about to reason about the consequences of actions in a very particular and very important domain of the recycling of electromechanical devices, where partners like Innsbruck, University of Göttingen, and KIT from the Experience project working with new partners here and also with the electro recycling company here in order to use actually this internal simulation and reasoning about the world and about object affordances in order to perform these tasks in industrial context. As I said, the project is very research-oriented, and still for me, one of the impact factors are how much knowledge has been generated by the project, also in terms of publications, which are available maybe for everybody to read. We don't know about, of course, the impact of these publications as in any other project, but this is a very important, still very important index from my point of view. You see here some of the numbers here, the publications resulting from the projects and the invited talks by PIs of the project in the last 5 years, but also the personal achievement similar to the sFly project here. 6 people of the project got their professor positions and are established researchers at their universities here. 2 fellows, several European projects of the PI, and 2 people of the PIs were actually in the founding board of EU Robotics or now Spark. That's for now. Thank you for your attention.
And it shows the importance of continuing also foundational research to feed in the pipelines. It's
yes,
so important.
yes, this is extremely important, and I hope that you and the Commission will find more money actually to support basic research. Both things are important, but we cannot do innovation and transfer to industry without this kind of basic research. What's done actually not only in this project, but in several other European projects, and hopefully more European projects in the future.
Let's fight for it.
Okay.
Yeah. Thank you so much. And then if you have just one quick question to conclude. Otherwise, I'm happy. And thank you to everybody for coming and for presenting the success of your project. And thank you for the attendance. So now it's a break, and thank you again. Bye-bye.